My name is Victor Moreno. I'm a distinguished engineer with Cisco Systems. I've been collaborating with Colin and the Nexus team on a series of different endeavors for a while now. And today I wanted to give you my view on how the internet has evolved and how it actually dovetails into the work that Colin and the team are actually doing here at Nexus. So it all started in the early 60s. There was a very interesting individual, Joseph Licklider, who back then he was between MIT, the Defense Department, and some private companies, but he was able to envision what the internet actually became later on, and he had this vision of a galactic network that was basically a pervasive network that would enable everyone to communicate with each other. It would enable computers to actually interconnect with each other. And back then, you got to understand, computers were things that existed in some bunker and were seen as very unfriendly and very far removed from what we did daily. So Licklider had that vision, and it's amazing because when you look at his memos and you look at how the internet has evolved, we keep actually bringing his vision into fruition and without even knowing it in some cases. So that's where the main concept started, and he was very well connected in the Massachusetts area back then, and as well as in the Pentagon, and he was able to influence some key players in DARPA back then. Amongst them was Lawrence Roberts, who actually led the whole effort of designing the ARPANET. But anyway, more on that in a second. So that was one of the key seeds in the birth of the internet. And parallel to that, the overall research community had been independently, on many fronts, had been coming to the conclusion that a packet switched network was something that was needed for computers to actually be able to interact with each other. So what we refer to by packet switched network is basically, if you go back in time, when you look at the phone system and how it worked, it established circuits. And if you look at each one of those boxes, think of it as just boxes full of little relays, and it physically would patch one pole to the next and do that consistently until it created a dedicated circuit between the phones. And those links that were used for that communication were dedicated exclusively for that one flow, couldn't be shared. So you were wasting a lot of bandwidth, but also there was no notion of resiliency, failovers, replication to multiple destinations, and so forth, right? So we had to move. It was clear that we had to move from the circuit switch paradigm to a packet switch paradigm. And the packet switch paradigm was basically one that allowed computers to talk to multiple recipients. So if you look at a web server, it would be impossible for a web server to fulfill its mission if it was circuit switched. So the network had to evolve to packet switch, and that didn't exist back then, right? So with this in mind, right, Lawrence Roberts and others went to work to DARPA. Roberts ran some experiments on connecting computers together. So it wasn't clear that there was anything to be gained by having two computers connecting to each other. So that sounds very obvious today, but back then it wasn't clear. So they went ahead and created a circuit over a phone line between Massachusetts and California. You know, talk about making your life hard. They could have done it within their lab, but between Massachusetts and California, they connected these two computers, and they actually got some interesting results in terms of the interactions between the computers and how they could optimize their processing. So with this, and with the conclusion that packet switching was the way to go, and all the influence on the need for this galactic network, right? So Licklider had actually convinced Roberts and others pretty effectively that this was a need. When Roberts goes to DARPA, they start this project, and he basically set the plans for ARPANET and presented them in 67 at DARPA. So to reinforce his proposal, in the same conference, groups from RAND and NPL also presented papers on packet switching and the importance of moving to that paradigm. So it was a done deal by then in terms of the concept. And then the thing that we didn't have were the switches that could actually do the packet switching. So an RFQ was issued for the building of an interface message processor. And back then, Bolt, Barakin, and Newman was the company that won that RFQ, and they produced an interface message processor. It was no coincidence that Licklider actually worked at Bolt, Barakin, and Newman back then. In any case, by the end of 69, the first IMP had been deployed at UCLA, and they were connecting to another IMP that shortly after was deployed at the Stanford Research Institute. So we can see here how there was a small 4-node network that grew from UCLA and Stanford into also UC Santa Barbara and Utah. And that was basically already providing some value, and some experiments were being run where you saw interesting things already happening, like buffering for using storage for them to optimize their graphic displays. So a simple version of some of the things that the 5G network today claims is going to happen when you have 1 millisecond latency to towers and things of that nature, right? So so you could already see the spirit of things, the way it was going. Now, by 1970, they were already expanded to the East Coast, with BBN, MIT, and Harvard joining there. And it became evident that they needed a control protocol to actually fiscalize or broker all the connections over these different links. And that was the network control protocol. So there was an individual named Vince Cerf, who's still around. He's a spokesman at Google. And he was one of the designers of this network control protocol. And that network control protocol was not just starting to be designed in the 70s, but it got adopted into the ARPANET in 72. Meanwhile, a gentleman by the name Ray Tomlinson at BBN thought it would be a neat idea to have a messaging system within the network, and that's how email was born. Initially, it was just there for people to actually exchange messages as they were experimenting with the network. So it was more of a built-in tool in the experimental environment that they were using, but it didn't take long. I mean, by 1976, even Queen Elizabeth of England was actually pushing the send button on her email. Obviously, this was something that was back then reserved to a small group of people, or the people who actually were affiliated with these networks. The modem was introduced in the mid-70s, but it wasn't until 1990 that there were commercial ISPs that would offer dial-up access to the networks. So the internet had already started taking shape, and it was an isolated network up to this point. It didn't allow other links or anything outside of ARPANET. It was assumed that it was highly reliable and that packet loss wouldn't happen, and therefore NCP was designed for that. And this all worked as long as you didn't change anything in the network. But you all can imagine that that wasn't sustainable. So right around that time, Robert Kahn joins DARPA, and he proposes the vision of an open architecture network. And what an open architecture network is one that is inclusive of not just the ARPANET, but also the packet radio network, the satellite network, and any network that could be built with any technology. In the meantime, talking about any technology, Bob Metcalfe at Xerox PARC was actually developing Ethernet, which later on led to a lot of proliferation of LAN networks. Now, with the open architecture in flight, LAN networks in flight. The commercial vendors took hold of this, and they started developing multiple protocols to offer networks. And these networks would potentially attach to a broader backbone eventually. So things were being understood better and better. And the open architecture network actually was key and critical in pushing the envelope in terms of technology. So when CAN proposes this, it became evident that opening up ARPANET beyond its controlled environment had a series of issues. And one of them that became evident was that there would be packet loss no matter how hard you try to avoid it. So NCP, it became obvious that NCP was not sufficient for what they were trying to do. So you can see here how this is reminiscent of what the internet is like today, where you have satellite links for long haul, and you have radio links for places where there is no cable coverage, and then it all links down to the wired network, right? So they needed to find a way to make all of this work together, right? So there were some ground rules that were set back then conceptually. So the networks should be autonomous, and should basically be autonomous from the perspective of the choice of technology. And we will see an example of that in what Colin is going to explain to you. They should not have to change in order to connect to the internet. So that is one key aspect of this, that you have a heterogeneous set of networks that are all connecting to each other. They're heterogeneous, but there needs to be some way of addressing the endpoints that is globally understood, right? So there are some commonalities, and TCP/IP provided that commonality, basically. The communications would be best effort, so you needed a way to do flow control and retransmission, and that's, again, what TCP/IP came in to provide. And of course, you needed the routers and the gateways to remain stateless. So they were black boxes. They didn't need to inspect the contents of the communication in order to forward. All they needed was a header that gave you the references on where to forward the traffic to. So all of this basically back then was pre the invention of TCP and IP and everything that we know about networking. So this was pretty clear thinking if you really sit for a second and ponder on it. And one thing that might be near and dear to this community is the fact that operations were federated. There was no global control, no central control of the operations, but this all basically was successful because the different entities were allowed to cooperate and by consensus operate the network, right? So this was a big advancement, and then it became evident to CAN that they needed to evolve NCP, and in evolving NCP, he enlisted Vint Cerf again, and they came up with TCP/IP, and the main design was ready in '73. It took some time for this to actually percolate and get adopted in the different into the different places in the network. A lot of it had to do with the insertion of a TCP natively into the Unix BSD stack, right? That was key. So being in the operating system, being embedded in the operating system is key to the adoption of these technologies. By '83, ARPANET was actually mandated to migrate to TCP/IP. So, and it was a flag day type migration, basically January 1st of 1983. You were going to flip the switch, and you either survived it or you didn't. And they had, nerdy T-shirts that actually said, "I survived the January '83 cutover." So there was a paper that was written by CAN, by Robert CAN back then, and some of the principles that he laid out on that are the principles that were the base for TCP, right? So pipelining and batch transmission, windowing, algorithms for loss detection and retransmission, and global addressing. Those are all the things that TCP/IP gives us. And one of the key things that he was after was, what is the best way to actually integrate this with the operating system, Right? What he was on a quest to actually enable the computers. The network happened to be an enabler for this, but it was a quest to enable the endpoints and make them communicate better. And the conclusion was that it needed to be embedded in the network OS, in the stack. So by stack, what do we mean by stack? What I have on the right-hand side of the slide is basically the OSI protocol stack. And if you go from the bottom to the top, at the physical layer, you have basically the wire and how I actually encode my messages in the wire. This is, am I turning on LEDs and turning them off, or do I simply have electric pulses? Is it just light if I'm actually beaming things in space? So this is my media. And then on top of that, for those of you who have dabbled a little bit in networking, we have the second layer, or layer 2, which is where Ethernet exists. This is my set of data link addresses. So your computer will have a hardware address, which is what is called a MAC address. It can be either on the wired side or on wireless. So when you're on Wi-Fi, your Wi-Fi radio actually has a MAC address on it. It follows an Ethernet-like standard. On top of that, we have layer 3, which is our IP layer. This is how computers actually find each other on the internet at a long distance over multiple hops across different networks, right? These IP addresses are unique to each endpoint and are the things that are routable in the broader internet. So you can determine different paths, you can find out where things are. This is really what makes the connectivity happen. And then, as we were discussing, we needed some mechanisms to actually do retransmission and detect losses, etc. So we came up with, Surf and Khan came up with TCP. Which had a windowing mechanism that would actually have a throttle back when there was congestion and actually open up as congestion eased, and it would adapt the flows to the behavior of the network. Now, that was very interesting, but it didn't necessarily apply to all flows. There were experiments being done on voice over packet networks back then, and it became evident that you didn't want to be retransmitting. Imagine that you lost a couple of or a second or so of what I'm saying, or maybe a fraction of a second, and then all of a sudden that comes back and gets replayed. It would basically garble up the voice and what I'm trying to tell you. So the human ear can actually compensate for a lot of this loss, especially in the sub-second range. So we needed something that would just stream the traffic through, and that would actually be more optimized in terms of preventing jitter and the impact of latency. And that's where UDP came about as basically a parallel to TCP for different applications, right? So when you find TCP or UDP, those are the type of things that you find. And then above that, these were basically the session and presentation layer were adaptation layers to actually get the application to leverage these services, right? Now, this was adopted. Why? Because it fit the bill technically. There were competing technologies, of course, and as all things on the internet, there's always a little bit of policy that needs to be put in place to actually get things to be adopted. So two things happened. The TCP IP stack was embedded in the operating system, which was Unix. It was the most widely deployed back then, and the government agencies mandated its use in their networks, right? Remember that this was all up to this point was basically government-funded networks, and they were either education networks or military networks, but that was where we were at. And at that point, the National Science Foundation started heavily funded. Back then, it was $200 million, which was a fortune in '86, and this heavily funded network basically became the focus. And over time, things like DNS showed up, but over time, ARPANET was decommissioned, right? And it gave way to the National Science Foundation network that also had a privatization plan. So once the NSFNet was privatized, we were off the ground. This was already in the hands of commerce. This was basically a commercially viable endeavor, and it had a life of its own by that point. Somewhere along the path, Paul Mockapetris came up with the domain name system, which is basically what translates your nexus.io to the IP address where that is served from. So what did we get along the path? Well, we got the concept of the galactic network, which is still evolving. We got packet switching. We got TCP/IP, and we got the notion of an open architecture network. So that's how far we've come, and what we're dealing with right now. And you could argue if the cut point is 2019, 2020, 2015, but where we're at right now is we've gone from the evolution of a connectivity-driven network, and that's all aligned with Licklider's vision. We've come up with data centers that are in the cloud, which is also in the memos, right? So AWS was in Licklider's memos back in '62. Imagine that. And I have to yet go through the memos to see if we can find the Nexus low Earth orbit network there. But the key thing is that operations have evolved, the network has evolved, and we are now focused on what can the network actually do for us as users, from a business perspective, from a creativity perspective, from a communications perspective. And in order to do that, a lot of what we do at Cisco, in order to enable those services without disrupting the connectivity that has been achieved so far, is we dabble in the notion of separating location and identity. So the TCP/IP that we got from SURF and CAN it basically assumes that an IP address is representative of both the location of an entity or an endpoint, as well as its identity. Right, but you can see how, because it has location semantics in it, if I move the entity, then the IP address must change, right? So this has a lot of repercussion in terms of how we actually can provide services. So what we've done is we've separated the location and the identity, and if you keep the identity fixed on the endpoints, then the network attachment points are the ones that represent the location of these devices, right? So think of us actually moving connectivity to space, to moving devices. So either the hosts are moving, or the actual network topology may be moving. So this decoupling is critical in actually continuing to achieve connectivity. And that's just one example of a myriad of services that benefit from this location identity split. So as we saw, satellite networking, it has been part of the internet for many, many years, but mostly it has been with geostationary satellites, and it has been in there to provide linkage between geographic locations that are very hard to achieve. But those satellites are basically predictably in one place and always in the same place. Now, when we go to low Earth orbit, the satellites are actually moving constantly around the globe, and they move in different orbits, right, in different rings, and the relationship between satellites in one ring and satellites in another ring is constantly changing. Furthermore, the relationship between the satellites and whatever is on Earth is also constantly changing. So they're constantly updating their list of neighbors, and that is in stark contrast with how the internet works today. The internet works today based on the fact that I set a node, you saw it in the diagrams, I set a node in UCLA, I put a wire that goes all the way to Stanford, and I have another wire that goes to Utah and another connection that goes to Santa Barbara. That's predictive. I'm not going to, these locations do not change, right? But now I have satellites and they're trying to connect to each other. So routing based on IP may not lend itself to that connectivity. So what do? Well, one idea, there's a lot of ideas, by the way. This is what's referred to as ad hoc networking, and there's an ITF group called Manet that deals with this. But one idea is that we can route based on GPS coordinates. And route as the crow flies. So if I know that Colin's computer is at certain coordinates, then I can beam my traffic in the direction of those coordinates. I don't have any guarantee that there will be a next node to pick that up, but with enough density, I can actually statistically provide those guarantees. So it's a local calculation that each satellite can make, and they can basically start beaming the traffic in the right direction. And then at some point you get to a satellite that that knows that it actually has a cone of coverage that includes that destination coordinate, and at that point you have basically gotten to the last satellite that you need to get to, and then you beam back to Earth, and now you've got connectivity provided here. So this is just one very specific example of the type of things that you would want to do in that network, but the idea is that you can actually still relate the IP addresses, because once you beam to Earth, you're going to have to switch based on IP. So you're still trying to get to an IP address destination, but you map that to GPS coordinates, and that's the location ID separation. So what we do basically, let's look at an example where the green robot is trying to talk to the red robot. Well, the red robot connects to a base station, and that base station is going to register with a mapping system. And when it registers with that mapping system, basically what we provide is the IP address of the base station, right? It's 10.0.0.1. That's the thing I want to get to. And I register the location of that base station, either in the form of an IP address, which is understandable by the existing ground internet, and also in the form of geocoordinates, which can be used by these mobile satellite network to get to the destination. So what happens is very, very simple. When a packet is received at the base station where the green robot is connected, I'm going to basically have my base station issue a request for the mapping information for the destination, which is 10.0.0.1. So I go request 10.0.0.1 from the mapping system, and I get back the locator information, which is the geo coordinates and that 169.8.2.1 address. With the geo coordinates, I then send my traffic up to space. So what you see here, I don't know if you can see my mouse, but right before the 20, right before we get onto space, we're simply sending an IP packet, and the IP packet has an IP header that has a source address and a destination address, 20.2 and 10.1. That gets to the base station. At that point, I do my lookup. I know that to get to 10.1, I need to send the traffic towards the geocoordinates that you see there. So at that point, I'm going to add an extra header to my packets, and I'm going to use that to switch between the satellites. And every time I get to a satellite, the satellite will know, oh, in order for me to get towards those coordinates, I need to go so many degrees north, east, west, or south, right? So I can point in that direction, send the traffic through, and then when I get to the last satellite, which will know that it has a coverage or a cone of coverage on Earth that includes those geocoordinates, I can then send it back to Earth. And when it gets back to Earth, I remove the green header, and I am left with my original IP packet of 20.0.0.2 to 10.0.0.1. And from there on, it's just networking as usual. So that's an example of where we're headed. And you can see how we're actually leveraging a lot of the heritage from the internet and basically playing into that open network architecture and really making it a galactic network per Licklider's vision.